All right, so what do we have? We're talking more about sound waves. First, a little review. What's a wave? So a wave is some disturbance in a medium that transports energy but not matter. But then I'm writing that. You're, of course, writing that. A disturbance in a medium that transports energy but not matter. The medium is the stuff that the wave passes through. And by disturbance, we mean the medium moves. Okay, so sound wave, we have, well, hopefully we have air in our atmosphere. And so these are gas molecules, nitrogen, oxygen, some other stuff. Hopefully not a whole lot of other stuff. And we breathe that in. And so when I'm moving my vocal cords, or, well, you're not listening to me, but you're listening to your speakers or headphones. So there's something in the speaker called the diaphragm that moves back and forth, and that bumps the air molecules back and forth, and they move back and forth and move. They bump into other air molecules, which bump into other air molecules, and so the sound wave goes towards your ear, and then your brain does some stuff, and it sounds like sound. Okay, so that's a sound wave. It's a longitudinal wave. Air molecules bouncing off one another. So, properties of sound wave. We have talked about these things: amplitude, frequency, speed of waves. And if we look at our wave over here, this would be our equilibrium position. And so you can imagine water waves, where if there were no wave, this is what the water would be doing, just sitting there. And then some is up and some is below and some is above, some is below. Okay, so the amplitude, this distance from it's the maximum displacement from equilibrium, and the frequency is how many waves would pass by us per second. So waves per second for frequency. Okay, in terms of sound, amplitude, so the height of the wave refers to the volume. This is a large amplitude. This is a soft amplitude. Or okay, so low volume, small low volume would be like this. That's me whispering. I don't know if you heard that. And then me yelling, which of course I do all the time, is like this. Okay, so we say that. Let's go back to our words over here. So amplitude is related to the volume, and then frequency is related to the pitch. High pitch, low pitch. And then the speed of sound waves. So in physics, we'll talk about 343 meters per second. And on the next slides, we'll see some stuff about that. So let's see, range of human hearing, we'll talk about in class. And you can just write this down for now, but here's what people say. From 20 hertz to 20,000 hertz. And there are problems with that, but we will see that in class. And so the rest of this stuff, just fill it in the successive slides, but I needed some space for some images. So let's proceed here. All right, so first, you should get this app. It's free, Tone Generator. We'll be using this in class. Pretty fun. All right, and then here's a little video to play. Before I start, this is the frequency. This is the play button, and this was just an online tone generator. Hey, oh. So here we are at an online tone generator. It shows middle C, so this is saying 261. Let's see. Oh, there we go. 261.62 hertz. A lot of times 256. Hey, I'm interrupting so it's not super exact. But anyway, this is what it sounds like. Bump up the volume. And then I'm going to, this is a times 2, so this is the next octave above. And the next octave above. Ooh. Okay, and instead of middle, so middle C, and then just below that, we have a B, and then an A sharp, B flat. So let's play a couple of those and see how they sound relative to one another. That's the C, B, effect, B, and then C. So the notes on the piano go from A to G.
So those are a couple
scale.
notes around middle C on the piano, and we will be experimenting with different frequencies and tones in class.
Cool, all right. So here is some data pulled off our interweb related to the speed of sound and air. So first maybe we could look at this. So the speed of sound and air definitely depends on temperature, and you can think of the faster the hotter air is, it means the air molecules are bouncing back and forth faster, and so they're more likely to transmit sound waves, so that kind of makes sense. Cold air, slow sound, hot air, fast sound. Yeah, all right. But this is the number we'll see, 343 meters per second, so this is room temperature. Again, that's degrees centigrade, and this is at sea level, so it'll be different for us in Mammoth. And it's actually kind of complicated. I think that we're going to find values that are, oh, I forget, even though we do this every year. Nice work, Torville. But let's see, here's some other things. Sound passing through air, glass, steel, water, and seawater. So notice how it's fastest through solids, and then medium speed, I mean this is pretty fast, but it's medium through liquids, and then slow, quote-unquote slow, through air, 343 meters per second, and that's something like 740 miles an hour. Here we go with some more. Let's see, temperature. All right, so we can compare different temperatures in air, and this is feet per second. America. Steel through hot steel is a little bit faster than cold steel. And let's see, hydrogen. Wow, that's fast. Okay, a lot faster than air, maybe because they're very light molecules. Although carbon dioxide, right, heavier molecules. Okay, that makes sense. And then just to refresh our memories, when we talk about the speed of a wave, this is vague, but it's related to the square root of the elastic property over the inertial property. And so this is like when we talked about waves in a string, the elastic property was the tension in the string, and then the inertial property, inertia meaning related to mass or tendency to resist acceleration, this was the mass density of the, mass density of the string. So when you're thinking about, what would the speed of sound and air be or something like this, these are the two variables that affect that, elastic property and inertial property. Okay, so now we're talking about, on the bottom left of page 1, we have constructive and destructive interference in space. So what we have here is two sound sources. So imagine two speakers, and they're some distance apart, and we have them hooked up to that tone generator. So they're playing the same frequency. It's a monotone, single frequency, and you are somewhere, excuse me, you are somewhere out here. So if you were at point C, the blue and the blue lines, these indicate wave fronts. So you can think about this as maybe a maximum or a wave crest. So do you see how at point C we have overlapping wave crests, so we'd have these waves adding together. This would be constructive interference. Whereas at point D, from the purple wave, we'd have a wave crest, and from the blue wave, we'd have a wave trough. So this would be like, let's see, here's blue, so we'd have a wave trough, and for purple, we'd have a wave crest, and here's our point D, and so they would cancel out. So theoretically, if you had, there's no, let's say you're in a soundproof room, right, so there's no reflection of the sound waves and whatever, you have two really good speakers playing one tone, you could stand right here and you would hear nothing, and you'd stand right here and it would sound very loud, and you could stand right here and it would sound very loud. That would be trippy. And this is sort of hard to make it work. We've definitely tried this in class, and I remember trying this in college. It's difficult to not get any reflection off the walls due to the sound waves. So here's a description of the situation where for point C, It's the same distance away from both sound waves, so the sound waves are in phase, and they overlap and constructively interfere. And then at point D, because the distance to point D is greater from this speaker, less from this speaker, all of a sudden they are out of phase and would destructively interfere. So this is an example of constructive interference and destructive interference from two point sound sources, we could say. Next up, bottom right, we're talking about beats. So constructive, destructive interference. And beats, this is something that's fun and easy to demonstrate. So when you have two frequencies that are similar but different. So similar but different frequencies will create this wah 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 sound. So we'll do this in class, but here's a visual representation of it. We have the blue wave and the red wave, and you see how blue, so we go crest to crest in a shorter period of time, so the frequency of the blue wave is higher. What do we say? Oh, so frequency of the blue wave is 60 hertz, red wave is 50 hertz. So we have constructive interference, they're overlapping, and then all of a sudden, by the time we get here, there's destructive, a trough and a crest. So this down here is showing the result of adding these two together. So we have loud, and then soft, and then loud, and then soft, and then loud. And it turns out that the frequency of the beats, so this would be loud, soft, you'd hear this kind of a 50, 60-ish hertz sound, loud, soft, and the frequency of this is the difference in the frequencies. So somewhere here I thought it said that the beat frequency, and that would be this, the difference in the frequencies. So that would be 60 minus 50 hertz. Alright, so I'm excited to see that in class. Okay, sonic boom. Oh yeah, Doppler effect. Alright, so Doppler effect is, well, maybe you know what it sounds like. If you don't, it sounds like neo. And so I'll say that once more. Neo. And so there's a high frequency and then low frequency as the thing passes by. So you can imagine, here you are standing here and there's a fire truck and it's emitting the sirens on, right? And as it passes by you, all of a sudden the sound changes. And so that should be intuitive to you because you've probably heard it before. And what happens with the sound is it's not the volume really. Yeah, sure, the closer it is to you, the louder it is. But what's actually changing is the frequency. So if the fire truck is not moving, it's emitting these sound waves. So these are these wave fronts, okay? Imagine it's emitting a single frequency sound. So we have an observer behind and an observer in front, and they hear the same thing. However, if the fire truck is moving, all right, this person up here, do you see how, so by the time the fire truck emits a sound wave, and then it has moved by the time it emits another sound wave, and then it is moved by the time it emits another sound wave, so the sound waves get bunched up together. And similarly in back, it emits a sound wave, and then it has moved farther away from that sound wave by the time it emits another one, so they get spaced out and back. So the speed of the sound waves in air is going to be the same for both of these people. So if the wavelength here, they're more bunched up, this person's going to hear more of them pass per time. So this person is going to hear a high frequency, and the person below, and behind, excuse me, is going to hear a low frequency. So when the fire truck comes towards you and passes by you, you get to be this person, and then you get to be this person, where you hear a high frequency, neo, as the fire truck is approaching you, and then neo, a low frequency as the fire truck passes away from you. All right, Doppler effect, and we'll see more of that in class. sonic boom. So you may wonder, well, so what happens if the fire truck's going faster and faster and faster, right? The speed of sound, so Mach 1 is actually only, what am I doing? Here we go. Mach 1 is only 740-ish miles per hour. So what if it were just a real souped up fire truck, right? They want to get to the fire fast. It's going 740 miles an hour. Well, it's more likely to happen with a jet airplane, but so here is the little red thing. This is the source of sound. That's our fire truck. Let's say we're way above, okay? It's not moving, and here it's moving pretty fast, and here it's moving at the speed of sound, right? And so what happens is it emits a sound wave, and then it travels with that sound wave, and then it emits another sound wave, and so they overlap and travels with both of those, and then it emits another sound wave. So this overlap right here, this is like resonance, where we get these overlapping sound waves, and it's actually very loud. So I remember the first time I heard a sonic boom. So this is now when the object is moving faster than the speed of sound, but you still get this complete overlap of the sound waves. And so here, I was in, I don't know, fourth grade. Here's our schoolhouse, and it was a space shuttle. And we thought it was an earthquake because the windows rattled. But anyway, so speed of sound, there's an overlap of sound waves, and they come down, and it sounds like this big kaboom. So that's why it's called sonic boom. And when we talk about Mach, so for example, Mach 2, that would be when the spaceship is going twice the speed of sound, and so, twice that would be pretty fast. And then, what we should also watch is Felix, the Red Bull skydiver guy, who turns out that the speed of sound is different really high up, so it's going to be less. So I think that he actually broke the sound barrier, because the speed of sound where he was high up in the atmosphere was actually much less than this. I mean, he was going fast, and it looked totally scary, don't get me wrong. Okay, let's see if we have anything else. All right. So here's not a fire truck, but a jet airplane breaking the sound barrier, and this is like those wave fronts, like this, where we're seeing this overlap. And what this probably is maybe high pressure causing water vapor to condense. So it's like kind of forming this cloud type thing. And then this is a photo taken from, I think, a bridge of some ships going through the water, and the waves pass slowly through the water, so it's a lot easier to see. But so this would be the equivalent of the wave front, where the ocean wave, right, is kind of spreading out like this behind the boat. So if these were sound waves, this would be the shock wave that me and my little schoolhouse would have heard. Okay.